Hi, ladies and gentlemen, this is Ms. Skokin. We are in Chapter 11 in our AP Statistics curriculum, and we're going to be talking about testing claims about means. Our learning targets for this section are to state our hypotheses, check conditions, calculate the test statistic, and find the p-value, perform a significance test about the difference between two means, which is putting all of those things together, and perform a significance test about a mean difference, which, if you remember, is that paired data that we've been talking about on and off, and determine when it's appropriate to use paired t-procedures versus two sample t-procedures. Remember, we always have to decide what kind of inference we're going to be doing at the very beginning of our question. Okay, so our significance test for mu1 minus mu2 starts always with we wish to test a claim, and we're going to be testing the hypothesis. The null hypothesis is that the difference between the two means is some hypothesized value, usually 0. And that means that mu1 is equal to mu2, which is another way of saying there's no difference between the two groups. Then we're going to have an alternative hypothesis, which is going to have an inequality symbol in it. When we talk about conditions, the random condition, we have to check both groups. Our 10%, this is only for sampling without replacement. If we've got a randomized experiment, no 10% rule necessary. And then our normal or large, what we called large counts when we were dealing with proportions condition, we have 3 different ways that it can be satisfied. The first way is if our data comes from a population that is approximately normally distributed. The second way is the central limit theorem when our sample size is sufficiently large, which means 30 or greater. And the last way would be for us to graph the sample data and have in a dot plot or a histogram and have it show no strong skew or outliers. Okay, so here's a problem. I'm going to have you pause the video and read the problem, and then we'll continue on. Has the mean number of hours Americans work in a week changed? One of the questions on the General Social Survey asked respondents how many hours they work each week. Responses from the random samples of employed Americans were recorded for 1975 and 2014. They're summarized here. We have the year, the sample size, the mean, and the standard deviation for both of the surveys that were conducted. Do these data give convincing evidence at the alpha equals 0.05 significance level of a difference in the true mean number of work hours per week for Americans in those 2 years? So the first thing that we're going to do is state appropriate hypotheses for performing a significance test. And of course, define the parameters of interest in the context of the question, and then check the conditions and see if they're met. So the null hypothesis shows the mean from 2014 minus the mean from 1975 equals 0. And it just said different. Are they different? It didn't say that we suspected one was greater or one was less. So we're going to go for our alternative hypothesis just with a not equal to 0. And then we define what each of the different mu's mean. So mu sub 1 is the true mean hours worked per week by Americans in 1975. Mu sub 2 is the true mean hours worked per week by Americans in 2014. And just a comment about this, in the past, it used to be good enough that we used the subscripts that were meaningful to the question, and we didn't have to go back and define so explicitly what each of those different variables was representing. That has changed recently, and we do need to be that specific. For the random condition, independent random samples of 764 working Americans in 1975 and 1501 working Americans in 2014, so we meet that condition. Notice it's a full sentence, and we're being as descriptive as we can be with the information that we have. For the 10% rule, 764 is less than 10% of all working Americans in 1975, and 1501 is less than 10% of all working Americans in 2014. And both of those sample sizes are large enough for the central limit theorem to apply, so we have met all 3 conditions. Our general formula is that the standardized test statistic is equal to the statistic minus the parameter divided by the standard deviation. And I'm going to apologize for that formula. I have no idea what's going on with that. It was okay before. Anyhow, we'll move forward. When the normal condition is met, we can find the p-value using the t-distribution with degrees of freedom given by, and we have two different ways. We have a big horrible formula that we really never use, and that's what your calculator will do for you if you run the test in your calculator. The other choice is we use the smaller of the two sample sizes in our two groups, and we subtract one, and that's the degrees of freedom. That's what we call the conservative approach. And those then will lead us, that smaller of the two values, degrees of freedom, and that will lead us to the correct p-value once we have our test statistic in table B. Okay. So, in the previous example, explain why the sample results give some evidence for the alternative hypothesis, and calculate the standardized test statistic and p-value, and then what conclusion would we make. So, for part A, we see that there's a difference. That's what we know. The X bar for 2014 is 41.91, and the X bar for 1975 is 38.97. So there's a difference. There's a difference of 2.94. We already know that. And that gives evidence that there's a difference, between the true values, because 2.94 is not equal to 0. It seems a little bit too obvious for us, but yes, we need to be that explicit. For part B, it says calculate the standardized test statistic and the p-value. So once again, this is a kind of messed up formula, but basically we're going to do the difference between the means minus 0, which is the hypothesis difference. That's going to be divided by the square root of the sample size squared. Wow, this is really rough looking. But you remember the calculator formula, or the formula off of your formula sheet, which is the square root of S1 squared over n plus S2 squared over n. Hopefully you remember that. And we end up with a test statistic of 4.88. Now, we have two different ways of doing this. If we use the degrees of freedom equals 100, which is the bottom of table B, and we find that the p-value is less than 2 times 0.0005, and we're doing the 2 times because it's a two-sided test, because we had a not equal to in our alternative hypothesis, and we get a very small p-value, 0.001. Now, if we did it inside the calculator, we would have a different degrees of freedom than what we used, which was 100, and we'd have a much, much, much smaller p-value. Either way, we're in the reject area. So because the p-value, again, either one, is less than alpha of 0.05, we reject the null hypothesis. There is convincing evidence of a difference in the true mean hours worked by Americans in 1975 and 2014. Let's take a look at a new example. Does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. Such observational studies do not establish causation. Remember that, that's super important. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy men who volunteered to take part in the experiment. They were randomly assigned to two groups. 10 of the men received a calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. The response variable is the decrease in systolic blood pressure for a subject after 12 weeks measured in millimeters of mercury. An increase appears as a negative number. Here are the data. So we have group 1 and group 2, which was the placebo group. Now, what we want to do is determine if there's convincing evidence that the calcium supplement reduces blood pressure. So that gave us a direction for our alternative hypothesis. Remember that because we have a limited volunteer pool, we can only generalize to that population. Okay, so our null hypothesis is that the difference is 0 or there's no difference between taking calcium and taking the placebo pills. And we define our variables and we define which alpha we're going to use, which is 0.05. We also have the direction here. We're doing calcium minus placebo. Next comes the plan part of it, which we're going to do a 2-sample t-test for mu sub 1 minus mu sub 2. We know that they were randomly assigned to one of two groups. The 10% rule does not apply because we are not sampling without replacement. And in order for us to check the normal condition, we have to graph both of the samples and see that there are no outliers or strong skew. Neither one of these look, there are a couple of points that are further away from the center, but in both cases, it's such a small group that it's hard to say that we have a cluster anywhere. So we meet the conditions and we move on to the do portion. So this is where, again, I apologize for the funny looking formulas, but the test statistic is going to be in the numerator, the difference between the sample values minus the difference between the null hypothesis values divided by the standard deviation of the two samples, so S1 squared over N1 plus S2 squared over N2. And we end up with a test statistic in this example of 1.604. The next thing that we want to do is to determine, using that test statistic value, what our p-value is. And whether we use the calculator function or we use the table B, we end up with a p-value of between 0.05 and 0.10. We were using 0.05 as our alpha, so that's going to lead us to a fail to reject conclusion. So because the p-value of 0.0644, I can assume that we got that from the calculator function, is greater than alpha of 0.05, we fail to reject the null hypothesis. The experiment does not provide convincing evidence that the true mean increase in systolic blood pressure is higher for men like these who take calcium than it is for men who take a placebo. So the calcium didn't help. Sometimes we are asked to interpret the p-value, and this is where we want to explain what it means. So assuming that mu sub c minus mu sub p, which is our null hypothesis, assuming our null hypothesis is true, there is a probability of 0.0644 of getting a difference, calcium minus placebo, in mean blood pressure reduction for the two groups of 5.273 or greater by chance alone, just by the chance involved in the random assignment. So this is an interpretation. Remember, we always have to assume that the null hypothesis is true and that the p-value is a probability of getting the values that we got in our sample or more extreme. So if it's less than, we would say less than. If it's greater than, we say greater than. And if it's just different from, we have to say it that way as well. When we run it in the calculator, we're going to do Stat.Test, 2Samp.T-Test, and the data input means that we've put the data into our lists, and then it's going to ask us what lists to use. Because we're using summary statistics, we pick stats, we put in the mean and the standard deviation and the sample size for each of the two groups, and we give the direction of the alternative hypothesis. We never pool with means. And what it gives us is the test statistic value, the p-value that we got, and the degrees of freedom that it used for the function. This is what it looks like on the TI-83 or 84 when we are using the lists of data. So we pick data, we tell it what lists, we still give it the direction for the alternative hypothesis, we do not pool, and then we can either calculate or draw. I love to draw because then it gives you the normal curve. But if we don't draw, it gives us what we need, which is the degrees of freedom and the p-value. We're going to call this part A, and we'll come back for part B for the remainder of this section. See you back in a few minutes.